Okay, so good evening, everyone. How are you guys doing? So, in general about life, or in general about about 576? Okay. Okay, maybe we can. So, some students came to my office hour, and maybe we can discuss some aspects of the assignment later on towards the end of this lecture. Okay. Um, yeah. So we are on like the fifth lecture for this course, right? So uh, just to kind of recap what all we did, we started with the regular classification pipeline, and that's it's basically a recap of what you have seen in previous courses. But the use is that you'll see that when you use PyTorch or TensorFlow, you need to think in terms of optimization as a module, model part as a module, cost function as a module, and then essentially you're doing a for loop or epochs or batch sizes or different batches of updating the parameters of your model, right? So that's why that first lecture was like that. So it's like think everything in a modular way, so that you know what to change. Sometimes the cost function has to change. For example, if you're doing not just object classification, the stuff that we saw for CNNs, but if you're doing object classification, but also you want a bounding box, okay, around the object, then your training data should have bounding box information. But your loss function will also change. It will not be just the cross entropy loss, but cross entropy loss maybe plus errors in bounding box coordinate values, for example. So that's just an example of thinking everything in terms of a modular way. Cost functions, there is some richness and understanding you need to have of how to define good cost functions, how to define models. Models part we'll see. Like for example, in Torch, you would primarily build on top of nn dot module or nn dot linear, nn dot con 2D or something like that. And optimization we haven't seen much except for simple gradient descent with fixed learning rate. There are variations, and there are also other techniques called atom and momentum and so on, but we'll see that later in the maybe in the next lecture or the lecture after that. Okay. So that's first lecture was just about setting the landscape of think everything in terms of modules, and this is actually true for many other models. So even if you change this to training your linear training linear classifiers, or training random forests, or training uh, support vector machines, you'll have the similar architecture. And different I guess ecosystems have different ways of thinking about these things. For example, if you are familiar with the scikit-learn library, there's a certain way that they have defined most of their classifiers, regressors, and the certain way that they create test train validation split and so on. So this is just a convention that I guess different communities adopt, and we'll see what I guess TensorFlow and PyTorch communities, how most of the code looks pretty similar except some changes in these modules, right? So second lecture we saw feed-forward networks, because those are essentially, I guess traditionally you would have seen artificial neural networks or multi-layer perceptrons. It's all the same name, but trying to make those networks have higher depth and also compose them with other types of layers. And the third lecture was essentially about certain type of layer called the convolution layer, and we understood it has lesser number of parameters compared to a fully connected layer, and it also has some nice properties that it's exploiting for image type of data, right? Spatial invariance and so on. And we also looked at a couple of other layers. I mean, one layer in this lecture called is a max pool, which is like just reducing the number of parameters so that the tensor sizes are not huge when you kind of get closer to getting to the score vectors. Okay. In the last lecture, we saw the notion of embeddings, right? So we actually just quickly run through some existing natural language processing models like topic model. We saw latent digital allocation. Okay, so that's one type of modeling, and it has its own field of study. Actually, it's in the field of probabilistic graphical models, and hopefully we'll cover few tidbits of that field uh, during this lecture, during this course. But we saw one key concept, which is the notion of embeddings, and they were nothing but if you had things which are not numbers already. So if you have features which are not numbers, which essentially means features which are categorical variables, things like movie names or things like strings or words, then you somehow have to have a numerical representation for them. And for each word or each such object which is not a number, you are ascribing a vector to it. Okay, and you're essentially learning that vector in the embedding. Uh, Learning that vector, and that vector is essentially called embedding. Okay, so essentially whenever you have objects like graphs or text, even characters or even whole sentences, you can always embed all of them into all these, I guess, combinatorial objects or things which are richer into numbers. Okay, which are essentially vectors. We Because most of neural networks is mostly about working with numbers, so you need to do that pre-processing of getting other objects to numbers or vectors, right? um, so that was last lecture, and today we're going to look at so at that point, since last lecture we kind of shifted away from images, we went to textual data. Okay, and the next lecture is trying to now work, I guess, between text and images. We're going to look at some sort of a temporal relation. So text has temporal relation, right? So a sentence preceding another sentence in a paragraph has some uh, temporal aspect to it. You wouldn't arbitrarily jumble the sentences themselves, or you wouldn't even jumble the words, because then the sentence would not make sense. So there is some temporal aspect, and RNNs are just some extensions of regular, I would say, feed-forward neural networks that capture, that make us easy to capture this temporal structure. Okay, so if you did not know RNNs, you could still, somehow, in an ad hoc way, come up with a nice model where you are able to capture temporal aspect. Okay, like I guess the thing that you should ring a bell is time series. Time series has temporal aspect. You cannot just jumble the stock prices across days and then still do some prediction, right? So you want to capture temporal aspects. So that's today's lecture. And what are the goals? The goals are first to kind of understand what type of prediction tasks we can do, which have these temporal structure, which I'm calling as sequential dependencies. The second point is what is an RNN? RNN is just a concatenation of a bunch of regular feed-forward networks. Okay, so that concatenation of a bunch of feed-forward networks for a few times, like 5 times or 10 times, is essentially what an RNN is. And so that's the idea that you need to get from today's lecture. Okay, that's the goal. So it should be demystified completely. It's just a copy of a feed-forward network or some variation like that, few times. The third goal is to get a little bit of more detail into what are some popular RNN cells. So when you copy, I said a feed-forward network, there is some popular variation called LSTM. So that's one block which you copy several times. So we'll get into the details of some, I guess, we'll ascribe some semantic meaning to how that network was designed. Okay, so LSTM is like a small variation of a feed-forward network, and there is some, I guess, semantic meaning that people ascribe to how they design that network, and we'll get there. That's just to kind of demystify when you see LSTMs or GRUs or variations like that in scripts that you see online or in your own exercises, then you should know what that block means. I mean, you don't have to code the inside of the block. You don't have to code that architecture from scratch, but you should know when you call, just like you call conv2d, eventually you're not going to write a convolutional layer from scratch where you kind of do a for loop and move your filter across. Similarly, you'll call LSTM block in your nn dot module, and so you need to know what's going on inside. Okay, and the last part is somewhat of a high level. We'll just look at some little bit more detail into what are these, this class of problems called sequence to sequence problems. Okay, actually, yeah, even something like language modeling that we saw last time using CNNs. Actually, not using CNNs. Last time we saw using Markov hidden, not hidden Markov model, regular Markov models, right? So to model language. So we'll see maybe that's an application of a sequence to sequence problem. Okay, that's a type of sequence to sequence problem. Any questions about the lay of the land so far? Okay. So okay. So as I said, today we'll try to cover, understand RNNs and LSTMs. And so let's start. Oops. Okay. I don't know how to hide that, but yeah. So let's start with, even and before I get to what are the blocks in an RNN. What is a sequence to sequence learning family of problems? Okay, so so here in terms of block diagram, we're just illustrating what are the different types of prediction problems you can have. So the one that should be very familiar to you is the one on the extreme left, which is the usual way to think about a classification problem. So you have some fixed size feature vector, maybe even think of shallow models, right? Some feature vector, maybe an image or a tabular data. So that feature vector, you pass it through a green block, which is essentially, for example, a neural network or some other logistic regression model and so on, and then you get some output. It's potentially a single vector of fixed dimension. For example, if you're classifying 10 classes in CIFAR 10, then your output is going to be 10-dimensional vector. Okay. So, but there are just extensions or just, I guess, bigger classes of problems, which are as follows. So here it's the second diagram on this slide is about the problem of image captioning. Okay, where the input is also fixed size. It's an image. Okay. And then the output is actually a caption for that image, and a caption is going to be textual. So the number of words in the text caption can change based on what's in the image. Okay, so let's say you could hypothetically magically figure out you had data which had images and captions, and somehow you trained a network which could go from image to captions. You need to kind of think of that. Every image will not have the same number of words as a caption. Okay, so an image can have different length captions, right? So that's something where the input is fixed, but fixed size, but the output is could change. Could be 2 words, could be 10 words, and could be 20 words. Okay. The third one is where the input is now variable, and this is the version that we've already seen last time, where we were doing sentence classification or sentiment analysis, where the input is a sentence, and then the output is just one label, whether it's positive or negative, or it could be multiple labels, not just positive, negative, but sarcastic, humorous, angry, different things, for example. So there the input, when we were looking at it last time, I made the sentence a matrix, right? But different sentences will have different length of different number of rows in that corresponding matrix, right? So the CNN architecture that we saw, the block should be such that irrespective of the size of the matrix in terms of the number of rows, dimensions is fixed, let's say, it should still be able to do its filtering operation and still be able to compute the same dimensional output scores. Okay, 2-dimensional, for example, if it's positive negative class. You should check offline whether the previous architecture we saw conforms to that dimensionality aspect or not. Okay. Next is many-to-many, where as usual, so input length is arbitrary, output length is arbitrary. So, for example, machine translation, which is essentially going from one language to the other, your language from English to, let's say, French, then the number of words in English for a sentence, the number of words in French for a sentence could be different. and you still need to make that prediction. So given the English sentence, you want to give the best French translation of that. Okay. And the last one is also many to many, but here, so in machine translation, you have to wait till the end of the sentence to know what the sentence means, right? You can't just looking at each word. You don't want to immediately translate, because then you don't know what the sentence actually meant, whether it was a question, whether it was an answer, whether it had something else coming up later part of the sentence. It's not clear. So this architecture, which I put star and circle, they're just differing in terms of that consideration. Okay. So these are, I guess, different variations of sequence to sequence problems, and we'll see a few more concrete examples after we go through RNN and LSTM. So the key idea of even forget about RNN, the key idea that we want to move towards now, since we saw some fixed size classifiers, is the notion of persistence, which is a notion of temporal correlation between some information and some information that precedes the current information. Okay, what do I mean by that? You can have, so if you look at the previous slide, if you look at sentiment analysis, the information from, let's say, the first word in the sentence, first word and the first few words in the sentence have a bearing on how you perceive the next few words in that sentence. So all I'm trying to say is that you don't want to think of this as a bag of words representation. You want to think of there is some temporal aspect to the sentence. Okay. So for example, the initial mood or negation words like not and other words like that, they influence what's coming later. Okay, so you can say this is a negative review, and then or this is a sarcastic review, and phrase it completely in the next few sentences. That means that review should be negative, right? So there is this temporal aspect that you want to exploit. And let me specify that with what's happening with the previous models. So let's say, think of a feed-forward neural network. Then you're basically doing things like this, right? So you're given a image, you're just classifying it as maybe just doing classification. So you're finding the object class in that image. Okay. Now think of a movie. Then you have a sequence of images. Now, what you classified in the first frame may have bearing on what you would like to classify in the next frame. Okay. Maybe if it's the same, maybe it's the same object persisting across frames or across images of that movie. Okay. So that's a very simple example of that you want to exploit temporal aspect rather than just doing per input classification, for example. Okay. And there are different ways to capture temporal aspects. One thing that you might have seen in traditional, I guess, shallow modeling, I guess not shallow modeling, but traditional models, is the idea of autoregressive moving average models. So just think of data being numerical now. Then you know how to capture temporal aspects. You can have pth order terms, and then therefore the pth number that you saw, or p days ago, the stock price that you saw, has an influence on the return that you'll see today, for example. Right. So that's a notion of a temporal aspect that you're capturing. Now, I like to think of you're going from x to a y, right? So x to a y hat, some prediction. What I like to think about what RNNs and what even ARMA models are doing is that they're trying to tease out the way, think of this x as a sequence of stock prices. Let's say price, 10 days ago, all the way to price yesterday. Okay, and now you're trying to predict returns. Okay, returns today. So both ARMA models and RNNs are explicitly trying to break your input observation. Okay, you're not thinking that as a single block now. You're literally trying to explicitly capture that. Okay, price 10 days ago may be not very relevant. Price today, yesterday may be more relevant. So you're capturing that in a linear fashion in, for example, an ARMA model, right? So what persistence that we want is that if it's, let's say, instead of phrases, these are sentences, then we want to know what information started, a few words ago. So it's the same observation, it's the same sentence. So X is a sentence now. Maybe it has 20 words. The word that appeared in the first three, in the first three words of the sentence, for example, it could be the gender of the subject in that sentence. Okay, whether it was he or she, you want to remember that. Okay, when you're processing and you're outputting something. Okay, so if it's relevant to the output. Okay, so when I mean temporal structure, I'm not talking about temporal structure across observations, which is like across sentences, or let's say across paragraphs. Here I'm talking about temporal correlation across words. Okay, that's the resolution I'm talking about. Maybe we can revisit this point if it's not clear. So what is the RNN architecture? It's basically start with a base network. Like a feed-forward network. In this case, what we'll do is actually start with a network where a network will have an input and an output, but we'll break that input and output into two parts. So it's as good as saying I have two inputs and two outputs, right? I can just break a vector into two parts and then say this is input one and input two, right? I can do that. So let's say I call that the base network, I guess, or what is the starting point. And then what I'm going to do is see there are two inputs here and two outputs here, right? I'm going to take one of the outputs and plug it back to the input. Okay, this is one way to represent it. Represent this idea that I have two inputs and two outputs. One output is actually being fed back as an input, and so this closes the loop, and there is an output, the usual output and the usual input. Okay, but what this actually means is just this, and this is what I was talking about at the beginning of the class, that you have some base or a starting point or a building block, a neural network. You're just making copies of it, but really, when I say copies, you're sharing the weights. Okay, and I'll get to that point in the next slide. You make copies of this building block. In this case, let's say I made 4 copies, or in general, it could be more copies. And I'm connecting the output, a part of the output, to the next input. Okay, part of the next input. Okay, so there is an exogenous input, external input at every copy. There's also an input from the previous copy. Okay, that's the two inputs, and there's could be a potential output in each copy, and another output, a part of the output is also fed to the next copy, succeeding copy. Okay, that's the idea. So what this does is, if now this bottom blue circles, that's your observation, that's your sentence. Okay, so you could think, okay, given the whole sentence, I can directly say whether it's positive class or negative class, or I can go word by word, do some processing. That block, we'll get into the block A soon. We can go word by word, feed some information as we move forward, as we parse each word, and then finally potentially classify. Let's say H capital T is our class, whether it's positive or negative. Okay, so that's the temporal structure I'm talking about. So maybe at the beginning there's a gender, or maybe a sarcastic word there that should have a bearing on what the sentiment is, for example, right? So, and I'm just saying that this sequence could be those movie frames that a few slides ago I was giving an example of, or it could be words. And this is called a sequence, collection, ordered collection of things. Okay, and in our case it will be vectors. Even if it is words, the embeddings are now vectors. Okay, so let's now dive into this base, or the building block A. Okay, so two inputs and two outputs. At the beginning there is, let's say, some null input. Okay, doesn't matter. Now, to kind of ease the notation, I'm just showing that I'm going to use square blocks to represent some neural network. Think of, you don't have to now visualize the internals of the neural network. Don't worry about the number of hidden nodes or the number of layers and all that. Let's say it's something that's taking input X and outputting some output Y, or input Z1 outputting some Z2. Okay, So there's a block. Arrows represent vectors. This represents a concatenation operation. It could also represent addition, but I'll explicitly represent addition as with a plus sign. So let's think of this as concatenation, and then this is just a copy. Okay. So here is an example of a vanilla building block. Okay. So here are 3 copies of the same building block. So let's just focus on the one in the center. Okay. It has 2 inputs. This guy, which is xt, and something output from the previous copy. Okay. These 2 are getting concatenated. Okay. So 2 vectors are getting concatenated. So for example, xt could be 5-dimensional, and the output from the previous block, one of the outputs from the previous block can be 5-dimensional. Then I get a 10-dimensional vector. That vector is input to this yellow block. Think of that as a neural net or some transformation that's taking the 10-dimensional vector and outputting a vector. Okay, that vector, I can, in this case, it turns out that let's say this vector is 5-dimensional. This is 5-dimensional. This is 5-dimensional. Okay, I'm just taking that 5-dimensional output and I'm revealing that to be the first output as well as I'm taking it as a second output as well in this case. Okay, so this is the copy operation here. But this is just, you don't have to copy at the output. You can have potentially a 10-dimensional vector and then first 5 coordinates is the output, and second 5 coordinates is what you pass on to the next block. Okay, so you can, in fact, so in this example, I'm assuming that the yellow block is actually is a simple transformation like this, which is tan h of w times previous ht minus 1 concatenated with xt. Okay, that's the vector plus bias. Okay, so if w's number of rows is 5, then the output is going to be some 5-dimensional vector. Okay, 5 cross 1. Tan h. What is tan h? Tan h is like a sigmoid or a ReLU. So it's an element-wise operation. Takes a number, outputs a number. And if you really want to visualize it, it's basically something like this. This is 0 and 1 and minus 1. Okay, it's like a shifted sigmoid. So as I said, it's a bunch of copies. So you can always create an RNN. This is written in NumPy, but this is not what you'll actually use. So you initialize with parameters. In this case, W's and bias are the parameters of that yellow block that we saw. And here I'm just defining a step where we are going from, we're basically talking about what computation is happening at each copy of this RNN sequence. Okay, you're basically computing the W times ht minus 1 concatenated with xt, and you're just linear transforming it, adding bias, applying Tanich transformation, and you're just storing that in h. Okay, and that's the example being done here. So this is a code version of what I just showed in the previous slide. So you do this for t is equal to 1 to whatever, in this case 3. Okay. Any questions about this?
What about the dimensions of the first output and the second input?
First output and the second input. So here I chose first output. So which output you're talking about? So let's say this is the output. So this is 5-dimensional, 5 cross 1. Okay. So in this example, the output is 5-dimensional. The first output, so there are 2. As I said, there has to be 2 outputs and 2 inputs. In this example, the 2 outputs are just the same. It's just a copy of each other. Okay, it's 5-dimensional. So input is, so you can see that's why this is 5 and 5. It's 10-dimensional input, and the Tanich is producing a 5-dimensional output in this example. So the number of rows here should be 5, and number of columns should be 10 in this W matrix. Okay. Any other question? Okay. So given that, I'm gonna kind of run through a language model that you can build using RNNs instead of those Markov, conditional probabilities that you could estimate directly as frequency counts in your data, right? So what we'll do is given a text data set, will model the probability of the next character given a sequence of previous characters. So let's give it at the character level, but the character level is not very critical. You can think of this as word level language model as well. Okay. For us, it's a question of there's a sequence of objects, whether they're characters or words, it doesn't matter. Okay. And let's say, in fact, I'm going to only look at a very small example. So let's say our vocabulary size is 4. We only have 4 characters. Okay, H, E, L, and O. Let's say we only have one training sequence, H, E, L, L, O. Okay, there could be more, but let's say this is the set. Then we can create 4 training pairs for this language model construction. Okay, so what do I mean by that? uh, if input is just H, I should be guessing that E is the next character. Okay, so language model is all about guessing what the next character is. Okay, so and if the input is HE, I should guess that L is the next most likely next character. Okay, and similarly, all the way to HELL, the next likely character could be in a different world it could be just space. In this case, it's O. Okay. Um, and what we're going to do is we have first characters, we have to pre-process them, and or not pre-process but just represent them. So let's just represent them as 4-dimensional vectors. Okay, because we have 4 characters, the simplest representation is a one-hot encoding representation. Okay, but you can also use word embeddings, but then the number of the dimensionality of the vectors hopefully is smaller than the number of how much vocabulary that you have. Okay, in this case the vocabulary size is the same as the number of the dimensionality of the vectors I'm talking about. Okay, so which means that I have 4 words in my vocabulary, right? So let's say H is this one-hot encoded vector, E is this one-hot encoded vector, L and L are this one-hot encoded vector. Then a particular version of this sequence learning problem is that given this vector, I compute this hidden this output, right? We saw from the A cell, the output is passed on to the next cell and also is being measured. So what is happening here? The output of the tan H. Okay, I'm going to choose it to be 4-dimensional. Okay, so in the previous example, I just picked 5 as a number. Here, the input is 4-dimensional. That's the word encoding. The output now I'm going to pick as 4-dimensional, where it's 4 because my vocabulary size is 4. So at each copy, I want to predict one of the characters. Okay, and the way I'm going to do it, I mean, I have 4 characters, so I'm going to have essentially a scoring function which says which character is more likely, or which character score is the highest. Okay, so in this case, let's say these are the 4 numbers. I want the number or the coordinate corresponding to the character E. So E is on the second coordinate. So think of HELO as like 1000 and 0100 and so on, 0010 and 0001. Okay, so this is the one-hot encoding for HELO. So this is H, this is E, and so on. Okay, so for the first output, H should predict E, so the second coordinate should be higher. Okay, that's what I want. I want to set the weights of this neural network such that the second coordinate is highest. Now I do the concat, so I have E, which is a one-hot encoded representation here. I pass the hidden vector here, which is in this case the hidden layer's output is 3, so it's not exactly the same as the previous example. So there's 2 weight matrices here. You're going from a 4-dimensional vector to a 3-dimensional vector, from 3-dimensional to getting four scores. Okay. So given these 2, E and this hidden vector, we compute some hidden numbers. These activations, and then those activations translated to scores should be such that now the third coordinate should be 1. Should be highest. Okay, because L is the next word, next character that I want given HE. Okay, and similarly you can see the rest of the preferences. So here we again need the third coordinate to be third coordinate score to be highest, and then the last one would be the fourth coordinate score to be highest. Yeah.
Does the magnitude of the number only matter or the sign also? Like there it is -1.
Oh, okay. This is an illustration. So, okay, let's tie it back to what we already know. So, why am I producing scores which are of the same length as the vocabulary size? Okay, I'm going to actually do a softmax transformation. Okay, and then that's going to be numbers between 0 to 1. Then I can actually do evaluate whether this transform scores are good or not by just using cross entropy loss. Okay, and I want to have the cross entropy loss low, which means that the scores should better be that they are the ones corresponding to the right character. Okay, so if my output class, so think of this as a 4-class classification problem happening at each copy, where the true label is E, and my output scores are these, or just the transform versions would be some numbers, and I want the E coordinate to be the highest. Okay, so there's a cross entropy loss captures that. So these numbers are just illustrations. Yeah.
Okay, so these are just illustrations. So
Yeah.
softmax will take.
Yeah, we'll change these numbers which are going from which are positive or negative. The softmax will put them into between 0 to 1, and in fact normalize such that the numbers add up to 1. Right? It's a probability vector. Then you compare it with the one hot encoded version of E. So that's essentially cross entropy loss. Yeah. Any other questions? Okay. And that's what I mean here. So you define cross entropy loss per copy. So now the overall loss function is actually the loss of the first copy plus the loss of the second copy plus the loss of the third copy plus the loss of the fourth copy. Okay, so that's the loss function. It's a function of the parameters, and the parameters are in this computation, right? So the yellow block in the previous slides, and you need to update those parameters such that this loss function is low. Okay, for this training sequence, and you can have more other words. So given a text corpus, you can always build a character language model like this. Okay, so what I kind of did not emphasize before, and let me get back there, is that the parameter, like the weight matrix. Okay, think of the tan-h layer, for example. There's a weight matrix in the bias. It's the same parameter across all these copies. Okay, so this is a different way of saying I'm doing weight sharing. So this is a different incarnation of, I would say, weight sharing. Okay, so I have different copies but the same parameters. Okay, so when when I'm evaluating forward, I'm doing a forward evaluation. So given the current weights, I use the same weights in every copy when I evaluate what I'm predicting in the first character, what I'm predicting in the second character, what I'm predicting in the third character. Now, cross entropy loss is a function of these weights, which are the same. So I have to do some gradient. When I do the gradient updates of these weights, I need to take into account, gradients get added because they are now part of two different loss functions. This we saw in the first lecture. Okay, when two gradients for two different loss functions, or when from the regularizer and the loss function, you have to update the gradient of W. You saw that we would add the gradients, right? So you have to do something similar here. And not just that, the copies also have the same parameters, so you have to update across copies. That's what's happening. Okay. Okay. So so this is just an example of why, so what is the long range dependence? So what is the temporal dependency that we're capturing here? Is that when the first first time you encounter L, with this simple, one data point of one, just five character data set, is that first time I encounter L, I should predict L as the most likely output, and the next time I encounter L, I should predict not L but something else. Okay, so there's think of it as like something like an autoregressive thing where if I'm considering the last two inputs, then my answer should change, for example, right? So that's the notion of persistence. So any questions at this point? This is basic, but worth thinking about. And and as I said, the summary is for this part is that RNN is nothing but multiple copies of some fixed neural network. So whatever network you designed previously, you can use that as a one giant modular block and concatenate it as long as you can take into account inputs and outputs properly, like the two inputs interpretation that I had. Okay. So it turns out that if you do this, when I say it, it turns out he's already smiling. So turns out if you do this, then there's this, because I'm sharing the same weights, right? So I want to do gradient updates. It turns out that the the usual procedure of learning the weights is very unstable. So people have figured out what are the best architectures, what are the best blocks to use as these as those building blocks in the RNN architecture. Okay. Um, so you can have any exotic, even a CNN with, let's say, 10 layers in there, but it turns out that there are simpler, well, I guess, uh, popular in practice and is, relatively easier to train blocks that have become popular, and that's what we're going to look at. And so one example of that is the long short-term memory cell. Okay. So by cell, I just mean that base block, the building block. So and these next 3 or 4 slides are just talking about why you know what is the motivation for a specific cell. There is this. So think of this R as a RNN function or a language model in our case. So advanced prediction, and then you'd say models. Okay, so here, in the previous, immediate information is being useful. So in that case, maybe with the vanilla, the architecture that we saw, where you use just a tanh activation. I mean, tanh is just, again, a choice. You could have potentially changed it to something else. Would be enough. But what if you had something like multiple sentences where initially you said I went to UIC, and then later on, in some later on sentence, you're saying I lived in, right? There, the language model, what should it say? Whether it's Chicago, I mean, even if it knows, even if it restricted yourself to cities, it's not clear which what it should say, right? So here, more context is needed. So you really want to capture some information, semantic information from long time ago. Okay, so that's what you're not able to capture in if you design an RNN from scratch or arbitrarily pick a base building block. Okay, so, and this is just an illustration of that. So that, like, this output depends on, let's say, these two, it's still fine. But if this output long time from now depends on, for example, the gender or the name of the person or some aspect of that, then it's difficult for the architecture that we saw, the one example architecture that we saw, to learn properly. Okay, to learn properly in the sense, get a good language model in that example. So, I mean, this is, I guess, the main point, that vanilla RNNs seem unable to learn these long-range information, and this is the one of the reasons why we're looking at a particular cell. Okay, um, and this cell tends to, at least empirically, it's been observed that it can capture certain long-range dependencies, and we will look at how the cell is designed. So the cell will have some neural network elements like transformations, nonlinearities, and so on. And there's a semantic meaning ascribed to different ways, different parts of how the cell was designed. And I'm going to now spend a few minutes talking about what the semantic meaning is. Okay, so just to look at the block diagram, the A cell previously had one yellow block, right? When I said the yellow block is like a neural network or some transformation like that, one layer of a neural network, for example. Instead of that, we actually have 4 blocks. Okay, 4 neural network style blocks, or think of it as 4 blocks. I just mean something like this: wx plus b. Okay, so this is like a linear transformation followed by nonlinearity. Let's say this is the simplest block, and then you have 4 such blocks here. I mean, the yellow objects, and they have some semantic meaning when they constructed this type of an architecture. It's actually really old, 1990s. So let's interpret this. Okay, so I'm going to use squares to represent that nn operation. I'm going to use circles to represent simple operations like add 2 vectors or multiply element-wise 2 vectors. Okay, and let's see. So in LSTM, so previously we had 2 inputs and 2 outputs, right? So a block A had some output two outputs on top right and top, and two inputs, right, left and bottom. Now, LSTM, on the other hand, is slightly different. So the key component in an LSTM is the notion of a cell state. Okay, so we are now zooming into just one block. Okay, there's just a building block, one copy, and the key vector associated with that copy is called the cell state. Okay, it's a vector. So uh, actually, this just focus on this. The input one is called C. I guess we are just representing it as CT minus one. So that's fine. So that this is called the cell state. This is a vector, and we'll essentially be manipulating this vector as we pass information, as inputs and outputs come in, as inputs come into the cell, and we're going to describe how we compute the outputs. Okay, so cell state is what we'll modify, and by cell state I just mean some vector. Okay, it's just designated, and we're calling it cell state. Um, so it still has two inputs and I would say two outputs, in the sense that input is of course some information right now, for example the current character or the current word, but it also depends on previous cell state. Okay, it also depends on part of, so instead of two inputs, two outputs, it looks like two inputs and sorry, three inputs and three outputs. Okay, but you can imagine that the cell state is the key ingredient. The other thing is just a slight transformation of it. So uh, we'll see what the other output is. Okay, it's just a simple transformation of the cell state. Okay, so there are some updates happening in the cell state. It's a vector. What do I mean by updates? The updates just mean, if it's a vector, there's going to be some multiplication operation on the vector or some addition operation on the vector. Okay, that those are the two updates in particular, which I'm representing as circles. So circle with a cross means an update is happening where the previous vector is getting multiplied element wise with the new with another vector. We'll discuss what that is, and later on, that whatever is the output is getting added with some other vector. Okay, element wise. That's essentially what's happening. Okay, so those are two operations that I'm going to do on the cell, this cell state vector, and the idea is to think of cell state as capturing the semantic information of the previous, whatever x number of words, for example, in a sentence. Okay, so the cell state vector somehow has to encode that, oh, maybe I saw a gender information, maybe I saw a place information, maybe I saw a positive sentiment related word or negative sentiment related word previously. Okay, so that's what semantically that we're going to interpret this vector to be. And the way we're going to manipulate the cell state, which is a multiplication and addition, requires another gadget which we call the gate. Okay, so we're going to modify the cell state. Those addition and multiplication that we saw. We're going to modify it. We're going to use a gadget called a gate. Okay? So what is a gate? Gate is a construction, or is just a gadget which lets information through optionally, which just means that I have a, okay, actually I have a, yeah. So let's say I have a vector v, and I want to modify that vector. Okay, so a simple gate can be something which is like a function which takes an input u, and depending on that input u, it outputs some numbers, right? So let's say v is a two-dimensional vector, so 3 and 5. Okay, u can be whatever dimension. Let's say sigma, a transformation of it, u is two numbers, 0.5 and 0.5. Okay, then the output is just an element-wise multiplication of 0.5 and 0.5. Sorry, element-wise multiplication of the first coordinate here and the first coordinate here. Okay, so a gate is essentially, for example, attenuating some coordinates of the input or amplifying the coordinates of the input. Okay, so for example, 3 and 5 are getting divided by 2 in each coordinate. So the output f of u comma v is, let's say, 3 by 2 and 5 by 2. Okay, So this is the operation of a particular gate. So I'm saying that a gate just attenuates information that its output can attenuate information of a vector. Okay, it'll do if you do element wise multiplication. Now, and actually this is just a more explanation of the same thing. What the reason why we use the sigmoid nonlinearity. So this part is just this. Okay, given you, linearly transform it, add a bias, and then apply a sigmoid transformation. Sigmoid transformation, the nice property is it's between 0 and 1, right? So if it is 0, then it's basically killing that coordinate. Whatever the number is, multiplied with the number which is 0, you'll get the number which is 0 for that coordinate of the input vector. And if the output is 1 for that coordinate, then it's essentially letting the number pass through, okay, of that vector. Okay, so that's the notion of a gate. And let's pick the first gate, which is and there's going to be several gates actually, in particular 3, but the first part of that LSTM is going to be to forget previous information, forget old information. So we have the cell state ct minus 1. I somehow have to transform such that some intermediate number, maybe c hat, I guess t, these are vectors. Okay, I have to forget some coordinates. Semantically, I'm saying I need to forget some coordinates, which just means I need to multiply. I need to take a gate gadget and multiply element wise, such that hopefully some coordinates are multiplied with 0, and those coordinates are kind of forgetting some information. Okay. It's just a semantic interpretation of what's happening with the vector. And in particular, the gate in this case, actually, do I have? Yeah, the gate is going to be sigma of w of ht minus 1 and xt plus some bias. Okay, so the input. So all I'm now specifying is the gate's input is going to be the current exogenous input, maybe the current character, current word, and ht minus 1, which is the additional input that we also get from the previous cell. So from the previous cell, we are getting ct minus 1, the previous cell state, as well as ht minus 1, which is just think of it as some slight simple transformation of the cell state, previous cell state. Okay. So given those two, do some linear transformation, transform, and with that I get this intermediate quantity such that the previous cell state I'm throwing away some information. Okay, that's a semantic meaning. Okay, and here is an example. Cell state may include the gender of the current subject, and maybe it's useful to predict, for example, the current pronoun, or use the correct pronoun. And then when a new subject is observed, then you want to forget what was the gender of the previous subject. Okay, that's the idea. And what I wrote in, I guess, the previous page is essentially the same as here. Subscript f here is just talking about, like, this is like a forget gate operation. Okay, so the highlighted portion towards the bottom left is basically taking ht minus 1 xt, going through this nonlinearity and multiplying element wise with the previous cell state to compute something intermediate, which is what I call c hat in the previous slide. Okay, so that's that part of that circuit, or that part of that base block. Next, we'll decide. So once we've forgotten some information, we're thinking about this modularly. We've forgotten some information. Now we want to add some information. Okay. Of course, if you want to add information, there's some sources of new information, which is the previous, of course, the previous ht minus 1, as well as some exogenous word as well. So it's basically the same inputs, but I have to manipulate them such that I can add some information to the cell state or that vector. Okay, and for that, there's going to be one gate and one simple neural network. So this actually is the the A that I was considering, the base block that I was considering at the beginning. It had some tanh operation, right? So it had ht minus 1 and xt. They were getting concatenated, and there was a tanh layer, and that was being output like this. So this tanh is the same as that tanh. Okay, almost it's the same interpretation, but there's an input gate which tells me what to add to the cell state. Okay. So this tanh computes something. So this tanh computes something which is can be added, and input gate modulates what information should actually be added. Okay. So let's look at uh, that this part of the architecture, which is that I have the same ht-1 and xt in the bottom left. I take those two, pass it through a gate. The gate is this thing over here. That's the gate sigma that computes in numbers, bunch of numbers between 0 and 1. So it can remember that number. That's I'm calling that as I subscript t. Okay, this is a teeth copy. That's why it's the I subscript t. And I'm passing the same these two ht-1 and xt to the tanh. That was the tanh from the first few slides. It gives me another thing, which is C tilde t. That's the candidate information that I want to add to the cell state. And what I'm going to do is use it and C tilde t and multiply them element wise. And what it's doing is trying to, C tilde t is my candidate new information, but I'm going to modulate it as well. I'm going to set some coordinates to be 0 if they're irrelevant, or keep them if they're relevant. Okay. And once I do that, then I add it back. Okay, where is this? Yeah. Once I do that, I can add it back to the cell state. Okay, this is the element-wise addition operation. So I did some forgetting operation before, and now I computed it and C tilde t. I multiplied them together, and then whatever was the intermediate quantity, I'm adding it to the cell state. Okay, so this is like a processed new information that I'm giving it to the cell state. Okay, so I first forgot something, and then I added some new information, which is processed because of this uh, input gate modulation. I guess modulation attenuation. Yeah.
How is it decided like which is relevant? We're trying to add some information.
Yeah. So this is just a semantic understanding of this architecture. How it's decided is completely data driven, right? So the only things that once you've trained this network, the only things that are relevant are the weights of these sigma, these gates, for example, the weights of these gates and the weights of the tanh function.
So like the example we were talking about, where I'm studying at UAC,
Yeah.
where should I live?
Yeah.
So in that example, like where will it pick up that Chicago thing?
So you need to have training data. So think of the language model example, right?
Okay.
So in the language model, if the pronoun for somebody, like there's gender information at the beginning of a sentence, then that information should influence, what you decide. Like, she did something, right? So that could influence what words come next. Okay. So if you want to predict, let's say the teeth round, or let's say not teeth round, but teeth copy, you want to predict maybe a verb, or maybe another noun. That general information may have influence, and that's being passed on through these vectors. Now, why would how is it happening in a data-driven way? Is that those weights here? Where's the weights? Like these weights here, for example, for the new information case, they are being learned in your training data, such that they can pick up and drop off appropriate information in a test example. So that UIC example, let's think of that as a test example. The weights are already tuned such that they know that they need to, given this particular sequence of words they have seen in the history, the weights are such that they can pick up the appropriate key. Yeah. It's a little bit, I guess, messy, but yeah.
So this one.
Yeah.
So this cell it basically gives an input basically an output at every stage basically. So it's a little
Yeah.
block which is being processed throughout the process, which stays throughout the process.
Yeah, so it's just think of this image, right? So we are just now digging deep into the building block. So the cell state is just this, this is like C1, this C2, C3, and so on. That's what you're modifying.
So
Yeah.
cell state will remain throughout the.
No, there is no storage here, no memory. There's just a computation. We are just interpreting parts of the computation, just like neural networks, right? There's no explicit notion of a storage. There's like a sequence of computations that I'm doing, but I'm interpreting what are the intermediate computations which are happening. Okay. I don't know if that answers. So any confusion so far, or everything is completely confusing? Yeah.
The idea for the new state is that from the previous state we're forgetting something and it's
Yeah.
new state, right?
Yeah.
That's gonna add, so that will depend on the weights.
Yes. 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 But how you learn the weights is to training example and keep that language model example in your at the back of your mind. Yeah. So where was I? So we looked at two things: how to forget and how to add information. Okay. That completely settles the issue of modifying the cell state. Now what we're going to do next is to figure out what this additional ht additional ht output is. Okay, it's just a simple transformation of um, the cell state. Okay, and what is that? Okay, so ht is the output. So we call ht, so cell state is just the key vector that we key vector corresponding to this copy. ht, you can call it as the output. Like for example, in the language model case, the output should exactly be the vocabulary size. Okay, so for example, if for example, in the character level language model, maybe 26 characters or 100 characters, whatever is the ASCII characters, right? 128. So ht has to be exactly that dimension. In fact, ht has to hopefully get transformed. Ht hopefully represents the score vector themselves, or maybe one more transformation to get to probability that this character is something. Okay, so that's a fixed dimension thing. Whereas the cell state is not, is hopefully captures something else. So there's a relation between ht and cell, and they need not be the same copy. Okay, so that's why we are talking about output being slightly different from the cell state. Okay, so and we're calling that output to be ht at this copy, teeth copy, and and the way we're going to transform is again simple, because we are using neural networks. We're going to look at whatever the cell state dimension is. Maybe it's 50 dimensions, and maybe my vocabulary size is 100. I need to go from 50 to 100 dimensions. I'm going to pass it through a Tanich linear layer. Okay, so basically go from some weight matrix which is 100 cross 50, and I have the cell state plus bias, and apply Tanich operation. So I'll get a ht which is 100 dimensions, which is the let's say, which is my vocabulary size.
What is the interpretation of XT? As in like
xt is the current xt
XT. What is the interpretation of it?
is the embedding of a character, for example. Or we saw the uh, several slides ago. Yeah, so just think of these as xt's. These red blocks at the bottom are xt's. Okay, the blue box at the top are the ht's. But yeah, blues are the ht's. Xt's are these bottom ones, one hot encoded or word embeddings of them. Okay, and in this example, there's only one. There's only ht or ht minus one being passed to the next copy. In LSTMs, the key concept is the cell state, which is also being passed to the next copy. There's also output, which is being passed to the next copy, as well as being output. Okay, that's the only difference. Now, which slide was it? Okay, so let's. So we looked at two gates. One gate was modulating forgetting of cell state. Another gate was figuring out what information to. There was some information being generated that was getting modulated, and then element wise getting added to the cell state. Next, the last part is we're going to define what the output is, ht, given the cell state. Okay, and that is what I was telling. So ht is just going to be some transformation of cell state, but that again will be modulated. And so first we'll pass a cell state, which is some vector, through the Danish layer. We'll get some intermediate vector, and then we're going to again scale it with another gate. So all gates do is just scale, right? I mean, given a vector, multiply element wise with zero, some number between 0 and 1, right? So it can kind of decide, like, for example, what parts of the cell state it can, if you want to output. If you want to output, for example, the simplest thing is, let's say the cell state is 10 dimensional, and uh, not all the 10 dimensions are actually useful. Then you can set some of the dimensions to be 0 through this gate, through this output gate, and that's captured here. So again, the gate is a function of ht minus 1 and xt. Okay. That's gonna element wise multiply with the transformation of the cell state. Okay. So tan h is taking something from here, which is the cell state ct, getting some intermediate vector, and element wise multiplying with some numbers between 0 to 1 coordinate wise, and that's the ht. Okay. So that's this ht, and there's a copy which is, I don't know why it's being passed on top, but it's not very relevant. Okay. So this is essentially the three parts of forgetting information, adding information, and defining what the output is. Okay. So I think the next slide shows the different parts highlighted and other parts shaded out. Okay. So forget, add something essentially modifies cell state, and I guess the modify and remember, I just said create new information, and output is just the creation of the output. Okay. So this we saw, it changes the set some coordinates to 0. This we saw create some new information. Okay. And then given the new information, modify, right, and create ht here output using ct as given the cell state. Is that fine? Okay, so that's LSTM actually. So any questions about LSTM architecture? It seems exotic because there are a lot of there are at least 4 different neural networks there are 4 different neural networks inside. There's 2 sigmoid layer, 3 sigmoid layer neural networks, and sorry, when I say neural networks, just think of this 3 sigmoid layers and 1 Danish layer. So like 4 matrices are there inside, and in fact, here, this tanh is actually not a layer. It's element-wise tanh operation. Okay. So actually, I should. Oh, that means that this is not correct. Yeah, this is not correct. Okay, doesn't matter. Okay, so there are four weight matrices and 4 biases that you need to estimate. Okay, and so that's LSTM, and it's somehow empirically people have figured out that this is able to capture is able to generate better language models than if you use a single tanh version that we were looking at in the beginning of this lecture. Okay. Now that's not the only architecture, right? That seems like a very heavily engineered, hand designed architecture. There are many other architectures that you can also have, but it's basically driven by intuition, by how people create these base building blocks for an RNN architecture. There are a couple which are very popular, and probably if you're just doing applied work, then you would want to pick one of these blocks. The second block is called a gated recurrent unit. Okay, it's the same idea. There's a bunch of gates and they modify information, but it kind of reduces the complexity. So LSTMs have this notion of a cell state. The version that I mentioned has a notion of cell state and an output. This one, gated recurrent unit reduces the complexity a little bit by merging some gates. So there's only so merges the cell state and the hidden state and combines the forget and the remember part. So somehow directly yeah. So there were 3 parts previously in LSTM. There was the forgetting and adding information. So it basically combines those 2 aspects in the network. And let's not go into the detail because the previous one was quite mechanical enough. I mean, it's basically just trying to interpret an architecture. Okay, and the weights are hopefully are data driven and well tuned such that they do capture the examples that I was talking about, where some gender x 5 words before is actually helping me predict the next word, for example, right? So that's GRU, and so we'll not go into the detail of a GRU, but GRU is something that's, for example, available in PyTorch, and you can use nn.lstm or nn.gru to build an RNN. Okay, so given these building blocks, I mean, RNN was just stretching, copying the blocks horizontally. You can do many other things with this idea. Okay, you can stack RNNs on top of each other, which just means that you're now copying spatially. Okay, whatever the block inside may have whatever complication it has, you're somehow tying the outputs to yeah, tying the outputs to inputs. Okay, so the outputs ht at this layer, okay, h0 at this layer is now the x0 for the um, layer above it. Okay, so that's just stacking, but it makes the whole computation, highly nonlinear. But you can see that they all should have the same parameters. Whatever the weights are, there are four weight matrices. They should be the same. Okay, so when you're training, there's a lot of gradients which get accumulated essentially. And those two that we saw, LSTMs and GRU, seem to be the best. Seem to be really good choices, and they essentially, and again tying back to the original idea, they have this. They hopefully can capture long range dependencies of your sequential data. Okay, so let's actually, yeah. So
When you're
yeah,
stacking the layers, will the stacks are different weight matrices or the same?
it's your choice. I mean, so here I'm using the same a block, but you can change that to some other block B, and so on. Yeah, but the thing is, I don't think you will go into such exotic architectures. This is an example of something that you can do, right? I mean, why do only do something sequentially? If you want further nonlinearities in your model, then you can do this. Okay, I think I'm not sure. So maybe for speech applications, people have looked at this stacked layer of RNNs, but I've not seen this elsewhere. So yeah, training for RNNs is the same as training for regular feed-forward networks, where there's just a weight sharing. The weights of the each cell copy is the same weights, so they have to accumulate gradients appropriately. So I mean, so I'll skip this slide, but this slide is accounting for dimension. So what is the dimension of the input and the output? Um, uh, for example, if ht is 2 dimensions, so you need to maintain hidden vectors as 2 dimensions, and cell state is 2 dimensions, then it is explicitly showing each dimension is being shown as a single line. Okay, so for example, there are 2 lines as input, so 2 numbers as input. Both numbers are getting multiplied by numbers between 0 to 1 to forget. Both numbers are getting added with some new numbers to remember some new information, and then both numbers are getting renormalized essentially between scale between 0 to 1, again getting multiplied by numbers between 0 to 1 to again for the output filtering, and then you have ht, which is again 2 dimensions. So any questions so far? Okay, this is a little bit of a laborious and it seems like a mechanical process, but this is just interpreting the insides of at least one cell. Okay, so that's the use. And what I'll do next is, should I take a break now? Okay. Okay, so let's take a break and resume at 7:25.
So freeze the layers and then only update the you can do that. Wait, can you release the
Okay, so in the next 15-20 minutes, let's look at some more applications of sequence to sequence models, sequence to sequence problems in detail, a little bit of detail, and then we can probably discuss uh, computational issues related to PyTorch or TensorFlow or the assignment. Okay, let's do that. So okay, so first example, so basically we'll go through like 3-ish examples. So first example is sentence classification. So we saw how to use a CNN last time, and we can also use anything else. I mean, we can just use naive based classifiers, for example, to classify positive and negative sentiment, right? That's a bag of words representation. So how to use RNN is basically you don't really care about the intermediate H0, H1, and so on. This ht should be exactly the dimension of your, what is it, your output. Sorry, the number of classes that you have. Okay, if it's sentence classification and 2 classes, then HT should be 2-dimensional. Okay, so and x0, x1, and x2 can be the vector representations of the words that you have in your sentence. Okay, for example, you can download the Glow or fast text or what is it, word2vec vectors, and use those vectors as inputs here. Okay, so the inputs are going to be, if it's Glow and for example, there's 100-dimensional version of the Glow vector embeddings. So x0, x1, x2, all the way to xt will be 100-dimensional, and then h0, h1, you don't really care. So but you do need to decide what the dimensionality is here. That depends on the weight matrix being in the. That depends on what are the weight matrix sizes that you're assuming in the LSTM, and this HT should be exactly, for example, 2-dimensional here.
So the architecture for the first block will be a bit different because it doesn't have any bigger.
You can feed in zeros. I mean something null basically. It will not be different. It will be the same, except you need to pass in something. Yeah. So that's a very quick example because I'm not going to spend too much time on sentence classification. Actually, there is. So okay. So on the syllabus page, not this one. Missed that. Yeah, on the syllabus page, there is actually PyTorch tutorial using RNN for sentence classification. So it's the same tutorial from the previous lecture. So in the previous lecture, there was a version of notebook for doing which implemented essentially that very popular CNN architecture for sentence classification. There's an RNN version as well in the same code base. Okay, so have a look at that, or maybe we can look at that towards the end of this lecture. So the next example is essentially is a very simple idea as well, straightforward idea, which is to do image captioning now. So for image captioning, the output is going to be a caption, which is going to be a sequence of words, right? And the input is going to be an image, right? A fixed size, whatever, 256 cross 256 or whatever, 294 cross 294, depends on the pre-trained network that you have. Okay, so the input is going to be an image. The output is going to be, let's say, two words here: straw hat, and then end as a token. So actually, a lot of NLP details I'm skipping out, but there are like things that you need to have, like a beginning of sentence and things like end of sentence and so on. Okay, so how do you do this? So you got an image, do the feature extraction, which is what you've been doing, for example, in your assignment. Get a, delete the last layer, for example, or last 2 layers, get a feature vector, and then that's the x0. That's going to be your x0. And oh, sorry, that's not the x0, but that's the let's call this h0. Okay, so the initial information. So one of the inputs to your RNN. So your RNN needed needs 2 inputs, right? So one of the inputs can be this, and then what you do is and then you are supposed to caption this image. So now you have the feature vector for the image itself. So that's the full information. That's the information vector that you have, right? You can transform it. So here we're just showing it as wi times h. Okay. You can start with a start token to start generating the caption. Okay. So start and the image vector together are the inputs for this copy of the RNN block, and the output is going to be a vector, which is going to be the size of the vocabulary that you have for your words. Okay, if it's an English word dictionary, maybe it's even 50,000 or whatever is a number of words, keywords in your vocabulary. Okay, so you're trying to predict. So remember the original character recognition, character language modeling problem, where I said the output has to be the same size as the vocab size. So here also the output size is going to be the vocab size, and hopefully you want to get high score on that coordinate which captures the right caption. So in your training data, you have images and captions. Okay, and so at the beginning, the start and the images feature vector together should output scores, which is going to be the vocab size, such that the coordinate corresponding to the first word of that caption has the highest score. Okay, that's how you want to train the weights in your network. Okay, so let's say we are not training this. Let's say those are frozen. Then the weights that we are training are essentially the parts of our RNN cell. Okay, the base block. It could be the simple block that we saw at the beginning, or the LSTM. Okay, bunch of weights. And I mean, here we're just showing that. I mean, so I'm just saying that this additional this initial input is like a different input. It could be it is a different dimensional thing than the could. For example, here, let's say we are picking this layer in this network. This is some old layer. So this is 4096 dimensional. You don't want to maintain a hidden HT, which is going from one one cell copy to the other. Sorry, one copy to the other to also be 4096 dimensional. So you can always do a linear transformation and pass it to the tanh for the initial cell. Okay. So back to your question, initial cell in this case is going to be slightly different. Okay. And then what you do is you could do a few things. You can actually, let's say you got your, let's think of the scenario where we have trained the network, okay, which means that I've trained my RNN. Let's say I fixed the weights, okay, somehow I've trained it. Let's come back to this point again. If I've trained it, then at test time, I can pass the test image, get the initial vector, give the start as always a starting token, and generate this. It's essentially going to be a probability mass function. Okay, this is going to be vocab size, and every coordinate is going to be a number between 0 to 1. Hopefully, the right first word would have the highest score. So whatever. So this is going to be vocab size, right? So from there, I can sample and get a word. Okay, so that's going to be my first word of the caption for this image, and then that sample I'm going to use it as input when I pass it to my next RNN copy. Okay. So maybe I sampled straw. I mean, in this case, then I'm going to pass it as input. Okay, maybe the word vector corresponding to that word as input, and the hidden vector from the previous copy. Okay. And similarly, so again sample something from here and pass it to as input to the next copy. Okay, so that's what you would do in at test time, and you'll continue to do this as long as you don't sample end, which may or may not be realistic, or maybe you sample it, maybe you terminate after a few fixed number of fixed number of rounds, which means that your caption you're getting like 10 words or 20 words and stopping. Okay, so the test inference time is clear, right? So how do you get a caption if you had trained the network, right? Now training the network itself, actually this point will come up later as well. So while training the network, you can actually train in a similar way. So you can train in a similar way. So in the sense of, remember how we trained the character language model? We said output is going to be vocabulary size, and we'll have a cross entropy loss per copy. Okay, that for maybe the right word here is straw, and there is a y vector which which will have a lot of coordinates, a lot of different scores for different words. But we'll have a cross entropy loss where we prefer the score to be highest for the straw coordinate and everything else 0. Okay, so you can do that. So we are defining a loss function, and you can follow the same procedure, which is sample the word from the y0 vector and process it through the next copy and get another vector. You can also do something else, which is, I know what the true caption word should be. I can actually pass that word as the input to my next copy. Okay, so I'm trying to be more, give more information to my network, in the sense that let's not depend on what it predicted for the first copy. Let me actually give the training data to my second copy to learn. Okay, and this is generally helpful when you're starting from scratch. Okay, and in the RNN part of this model. Okay, those are the two points I wanted to make. Um, so let's look at a slightly different application, which is, instead of image captioning, now I want to also make input variable length, which just means I'm going to look at a variation like translation. So we saw we saw machine translation where we were going from, let's say, English to French. Then the number of words in one language and number of words in the other language is going to be variable, and it's going to vary across sentences and so on. So there are many different versions which they all have the same structure. For example, there's a question of certain length and there's an answer of certain length for speech, and we'll see speech a little bit later. Same thing with translation, but here I'm gonna just ground it on a specific, another stylized example. Let's say auto reply. So you've seen auto reply in, I guess, Gmail, right? So basically it takes it passes in your input email, and given that input email, it generates a string, right? And it gives you a few options, and you pick one of them, right? So the first version is gonna, so how do you generate this variable length outputs, right? So there are different ways to do it. It's and it's going to be a departure from the RNN architectures we have seen so far, in the sense that there's going to be two parts to this problem. Okay, actually not there, but let's say last part is this. First, I'm going to parse all the input words. Okay, pass in all the input words. The outputs at that copy, I don't care. I'm not doing any cross entropy loss minimization there. I only care about the last. Once that sentence ended, once that email ended, okay, I generate some vector, final vector, right, output vector of that last copy. Now that vector is the encoded state of this whole email. Okay, so this part, actually, this whole whole part, including the last, let's say, last state, that part is called the encoder. It just encodes the whole input sentence into some vector. That's what essentially has happened, and this part is essentially an RNN. Okay. Now, given the encoded vector, okay, I mean it's terminated by an n token. Given the encoded vector, now I'm trying to give that as an input to another RNN. Okay, where the RNN's input is a single vector, like HTML or whatever, 100 dimensions. But starting from the 100 dimensions vector, I need to generate a variable length output. Okay. This we have seen. Image captioning was essentially starting from a image vector, 4096 dimension vector. We have to create a caption, right? So here it's just very similar. Instead of the input is not, the HT is not directly a feature extraction from an image, but it's actually the encoded or the output of a previous RNN. So I've basically concatenated two RNNs, where one RNN has variable input but single output, and the second RNN has one input and variable output. Okay. And of course, like if I'm outputting things, these have to be vocab size predictions. And here I can, in my training data, I'll have to do cross entropy per copy. Okay. Any questions about this example? What did I do? Yeah. So, okay. So the second version is again not copying, but like inspired by the previous image captioning example. I'm gonna actually help my RNN. So actually, previously, even for image captioning, I had mentioned that I can actually pass in previous word as a input to the next copy, right? Actually, in the first version, I did not do that. Actually, I was just showing that given the starting state, I'll just estimate IM, and given the hidden state, next I'll try to estimate fine and so on. Okay, but this is the standard, right? So we saw it in image captioning. We can actually, at least in training, we can give the true word itself, or given a distribution here, sample a word, give it to the next copy, and generate the output. Okay, so that's the only difference. And as I said, this part is encoder, and the other part is and the part on the right is decoder. Okay, so there is one more nuance, one small nuance. I mean, this is just a way to kind of give you an idea that it's not enough. So you have to do a little bit more, which is that uh, let's say at test time, as an inference time, you've already trained your network. So you have an input sequence, the some email. Okay, you first output. You start some email, you processed it, you got end of the encoder. Now you're generating words, right? Response words. Now maybe you output some probability distribution. You can sample from it. That could be your first word of your response. But you can also take the highest probability. You can take the word with the highest probability that that word has. Right, one of the words will have the highest probability of or the highest score. Just take that word, and then feed it as the input to the next copy. Okay, that's the highest probability word as the input to the next copy. Because if you sample, then maybe you are picking a low probability word with some probability, and then you may be derailed. Okay, so you can do that. Um, Given these two, you deterministically pick the coordinate or the word with the highest probability. Then you got some other output, and keep repeating this. Uh, Picking the highest probability word at each copy is a greedy procedure. Okay, and there is an I would say some sort of an amplification of mistakes. So if you make a mistake early on, it kind of fails the rest of the response is going to be very suboptimal. Okay, so a small trick here is what is called uh, beam search, or essentially just it is about maintaining several candidates as you keep generating parts of your auto response, automatic reply. Okay, what do I mean by that? So you start with an input, okay, and you generated your first word. What you do is, you're starting to generate your response. So in the first word of your response, maybe you can generate not, maybe you can pick not just the top more, that word with the highest probability. You pick the top three words with the highest probability. Okay, so let's say like k is 3. Okay, pick the top three words. Okay, so these are the three words. Let's say hi, yes, and please. And then you actually pass all three words into the next copy and get the top three words in the second level. Okay, so for hi, maybe there's three things here, and three things here. Okay, and you can see that the moment I keep three words, there's a branching factor of 3, and so I'm exploding in terms of the number of choices. But what I can also maintain is that when I pick this word, I can also remember the probability with which that word was, the probability corresponding to that word, right? So for the three words, I can copy the probabilities for the corresponding word at that level, uh, whatever that index, right? Um, so what I do is I multiply this probability. I keep a track of the probabilities for each path. Okay, so like please I. Okay, so please maybe was supposed to be output with had a probability value of, let's say, zero 0.6, and I had a probability value of zero 0.5. Then you multiply those two. Okay, for each path. So here you have 9 choices, right? At the second word level, you have 9 choices, but you also have the product of the probabilities of the two words. Okay, so those products you kind of again sort and drop the ones which are drop the last 6, and then you can keep the top 3. Okay, top 3 two phrases. Okay, and you can, so this is just a way to kind of not be too greedy, but also consider an initially suboptimal word, but hopefully, as it becomes a phrase, it's actually a much better phrase to respond with. Okay. Yeah. Yeah. So there's some issue. I mean, so the version that we saw also still has some issue, but we're not going to discuss this here, which is that I'm somehow, maybe the email has like 3 paragraphs. Okay. And I'm condensing the 3 paragraphs into maybe a 100-dimensional vector or whatever, 50-dimensional vector, or maybe even a 1,000-dimensional vector. That's like, it's not clear whether that 100-dimensional vector is going to capture all the semantic information in the right way so that I can generate the right response, right? So there are ways to train networks where you can do better than what is this particular encoder decoder architecture that we have. Okay. And that's through this trick of attention. Okay. uh, Attention just means that when I'm trying to generate a word, I'm not I'm not only going to look at the last output, last copy's output in the encoder. I'm going to look at all outputs of the encoder. So now I'm going to keep track of all outputs. Okay. And selectively focus on those outputs which are relevant to my current prediction. Okay. So that's the semantic interpretation of what attention trick is supposed to do, but the implementation details we'll skip today. Okay. It's just a way to say that, okay, why should I only take the last encoder's last output as the input to my subsequent decoder processing. I'll keep track of all the outputs and selectively pick those outputs depending on which part of the response I'm trying to respond with. Okay. So this is quite relevant for machine translation, where maybe the first few words are relevant for the first few words of your English, are relevant to the first few words of your French. So you would prefer the hidden vectors to be related to the first few words rather than the fully processed final word, fully processed full sentence. Okay. So that's it for the auto reply and slight variations of that. Now I'll also quickly mention speech transcription, because this is almost the same as before, except how do you work with speech data. So I'm just giving a couple of, I guess, spending a slide on like people who have not seen speech data. It's not really complicated. You can actually work with the same architectures that we have, but you have to do one pre-processing step. Okay. And okay, traditionally, okay, let's just to give you a brief idea. So before using like RNN type of architectures, we saw that we can use a language model. We can build a language model using RNN. We can also build a language model using just Markov model assumption, right? We saw that in the last lecture. Similarly, with speech, you can actually again do something like a Markov model, which is, or you can also use RNN here. But traditionally, historically, I would say 5-10 years ago, people were constructing interesting language models. So these were like hidden Markov models, they are called. And so basically Markov models. And then the acoustic model would be some sort of a Gaussian mixture model. Okay, Gaussian mixture model means a model where given the word, how would the output sound? It's like a mixture of Gaussians. Okay, so this is basically given the word, how is it pronounced? Okay, it's going to be some, there'll be different pronunciations, so there'll be a lot of variation. So that part people use to model it as GMMs, and this would be HMMs. Okay. These are both graphical models. We'll see if we can get to that during the course. And lots of feature engineering. That's how people used to do text to speech and speech to text. Okay. But now you can actually use the RNN encoder decoder architecture that we just mentioned in the previous slide. Essentially, is the backbone or is the starting point for building even speech transcription solutions, right? So like Mozilla's deep speech and Baidu's deep speech variation, something like that. So how do you start? Like speech data is essentially actually looks like this in in terms of time, as a function of time. You actually have some sensor which picks up magnitudes, right? So it basically it looks like this in time dimension. So you're measuring, and it's symmetric across the axis. You're basically measuring magnitudes across time. Okay, so this is the speech data in time, and and it corresponds to, let's say, this text. Okay, hi, how's it? So you want to go from that speech to text. Okay, so given that speech, that's a sequence, input sequence. In this case, it looks pretty messy. It looks like noise, but it's basically, if you think of an XY axis, there's one number per timestamp, and these timestamps are very close to each other. Okay, and the output is a sequence of words. Okay, now the way people generally go from this one-dimensional data, time versus some magnitude numbers, is to actually transform it to what are called MFCC features. Okay, and these are essentially features in a different domain. Like a transformation just means going from some domain to another, right? So in particular here, you're going from a time domain to a frequency domain. Okay, so there's some time frequency duality in play here, but we don't, that's not very important here. What is important is that you look at parts of this speech signal, okay, sequential parts of the speech signal, maybe 16 samples, 16 samples, 16 samples in time. Those 16 samples you essentially transform, think of like Fourier transform or variations of that. So MFCC is one such operation. So you get a vector. Okay, so that's the vector x0. Let's say there's a vector x1. Let's say vector x2. So you keep moving forward in time, and you somehow transform this data to a frequency spectrum data vector, and then that's the input to your encoder. Okay, and then the rest of the process is similar. Okay, except that here you see that they have used the two-layer RNN that you had asked the question before, right? So that's an example of speech transcription. I guess extremely, like, a lot of details missing, but this is the core idea. Okay, this is not the only idea. There are many different ways to do speech transcription, and it's also true for language models. There's also a question about whether LSTM, there could be other things inside LSTM like dropout and max pooling and so on, or multiple layers. You can have those things. But empirically, in practice, people don't really change those building blocks for RNNs. They focus on like stacking. They don't change inside the base block, but they kind of stack things on top of each other and so on. So things like bidirectional RNN just means you do computation in this way. You also do a computation the opposite way, and then some aggregate and get some final encoded vector, and then pass it on to the decoder. Okay, so these are all variations that people look at. Any questions about so far? So those are the few examples that I wanted to give about RNNs and how they're useful for sequence to sequence type of problems. Okay. So you can also do, you can definitely do time series analysis. Okay, time series models are essentially like your inputs are numbers, and you want to predict one final number each day, right? So that's the model that we saw, where essentially the encoder model, right? So you can have previous prices and one final output, which is the return for today, for example, right? So any questions about the applications? Yeah.
Actually, the output at every stage,
Yeah.
it is going to be having the dimension of the size of the vocab we are using, right?
Yes. In these examples, yeah, this is the dimension of the vocab.
So that would be like a huge column matrix
Yeah.
with all the words and
Yeah.
the probability.
Yeah.
So that would be like really high computationally.
Yes, it is. It is. So vocab size is it's a limitation. I think somebody was referring to sparse cross entropy loss. Maybe that helps computing the loss, at least in training time. If the vector is sparse, hopefully. Yeah, I'm not sure. So, but it is of high dimensions. Yeah. Any questions? Okay, so basically, just to summarize this part, I want to have some time for assignment questions and so on. So we motivated when RNNs can be used, understood some internal workings of the RNN building block, basically LSTM or if you're inclined, look at GRU. And we looked at some minor details, I would say high level details of sequence to sequence applications. Okay. Uh, so now, actually, what I want to do is, several of you had questions about the assignment, so I want to spend some time on the assignment, or we can talk about also basics of PyTorch that we kind of, some of the students and me discussed during the office hours. Okay. So how is the state of affairs with the first and second question of assignment 2?
Stuck.
So we can actually so because of feedback, I've not released assignment 3 yet. Anyway, I mean, because your deadline is tomorrow, I've not released it. It's going to be on RNNs, so assignment 3. Because I think the next exam is pretty soon, so maybe the number of questions will be smaller. But let's look at assignment 2.
What kind of exam can we expect?
So each slide deck has a bunch of, sample exam questions, and each, so you can look at what are the learning goals, right? So you'll be quizzed on the learning goals.
So like,
You need to-
it will be conceptual, not like proper method. There are few equations, but there will be conceptual.
Yeah, yeah. So any questions with the first assignment question, fine tuning and feature extraction?
Yeah, we're fine tuning the runtime is very high.
Yeah. So okay, so fine tuning. Yeah, for ResNet 18 also the runtime is high. It should not be, ideally.
I tried running it for just 100 images, it ran very fast, but when you give the file like 50,000 images, it's not.
So what's happening with the? So we had this. CNN. So okay, so this particular, so we saw this. So this was given in lecture 2, right? So here the data set size is small, right? What is the size? 100 images, and here they are able to show that they can fine tune, although they're using ResNet 18, so they still have lots of weights, right? What is the size of the? Did anybody type nn dot parameters and see how big was the?
I think the final layer is 512 features.
Yeah. So fully connected layers are the bottleneck essentially because there are too many weights to train there.
But we're replacing that with the two, either 1,000 layers. I think I did.
Yeah. So you're replacing in this example they replace it with a 2 cross 512 weight matrix essentially, and in your case you have to replace it with a 10 cross 512 matrix. That's fine, but I'm trying to understand why the training time is large. Is it because you're batching properly, or I mean, are you guys using batching? I mean, first of all, are you guys using the GPU servers? Okay. Uh, you can try increasing the batch size. I mean, so you should increase the batch size enough so that you are, your batch size should influence, you should keep the batch size high enough such that the GPU can take that much of weights and batch into its computation. The moment you increase the batch size, you will beyond some level, then you will see that you'll be erroring out because of memory requirements. Okay. Um, one I guess solution is to not fine tune the initial layers, by which I mean you have to delete, I mean not delete but remove them from the parameters that require gradients. Okay, so you need to set somehow the required gradient to be false for the initial layer parameters. Okay, and since all the layers have names, you can figure out how to set how to freeze them essentially. Okay, try that. I mean, first of all, try, of course, so even before fine tuning, freeze everything and just tune the last layer, which is 2 cross 512, right? So you should know what the timing requirement for that is, and then look at slightly extending to the next immediate layer and so on. So any questions about the second assignment? Okay, first one. Yes, let's go. Let's finish the first. Yeah.
What is the expected accuracy for the test data?
That benchmark I don't know. So what is it? It's a 10 class classification problem. So I don't know what the benchmark is. So you can. So there was a link, right? Oh, maybe I'm not sure if I shared it with you. There is state of the art. There's a website which tracks the state of the art numbers, classification numbers for many of these standard data sets. But we are not chasing state of the art numbers here. We just want a working solution which definitely guesses better than random. So here, because the classes are the same, random guess is 1 by 10. Okay, with 1 out of 10 chance you're gonna guess it correctly.
Better than 10%.
Yeah, I mean because the classes are the same here. Okay, that's with naively not doing anything, right? That's random guessing. So that should definitely be a benchmark. So you cannot be doing worse than that. Okay. Any other question? Like even if you train a subset of the data, you'll do better than 10% for sure. Okay, so if data size is a limitation, I mean if it's influencing your training. Okay. Yeah. So what is the? Is there any question? Any other question for the first question? Yeah.
So for the top 5 and bottom 5 predictions, we basically just get the probability of them and just take the maximum and the minimum for each class.
For each class, subset the data to get the observations corresponding to that class, and yeah, this is what he said.
And when you say compactly, you mean like a graph with 5 features for each class together?
Yeah, it's just that if you call one cell per image, then it'll be like too many. It will be too long in your notebook. So yeah, I mean just use the matplotlib subplot, plot or subplot, so with appropriate grid size. Okay.
So, basically, using this called portion make grid.
Yeah, you can do that as well. Yeah, if you understand the make grid syntax, then you can use that. It's not very necessary. Yeah. Any other question about the first part? Okay, so there were several questions about the second part. So let's see. Is there any question for the second question? Yeah. 2.2.
No, the
Optimize.
gradient within 5.10.
Yeah. So this is where. So how many of you have gone through a tutorial for PyTorch or TensorFlow? You have. Okay, so a few of you. Who has not gone through a tutorial for PyTorch or TensorFlow?
It was there in the last assignment.
Yeah, it was there. Oh, was it? Was PyTorch there in the last assignment? Okay, I mean, so TensorFlow in the sense you just use Keras, right? So it's not really you're using TensorFlow. Did somebody actually use TensorFlow directly? Okay, you did. Keras, right? So Keras is okay. So first of all, the second part. So I guess optimizing this function is something which is a little bit non-standard. It's not a neural network. I mean, it is a neural network in a sense. You can actually. So this problem is about collaborative filtering, item collaborative filtering. Okay. So if you ignore the these bulleted questions, it's all about okay, I have data about movies. Who watched what movies? Can I make movie recommendations? That's a business question. Now, to do so, you can do all sorts of collaborative filtering approaches. You can also do other regular feature engineering based predictions of what would be the most likely movies to recommend. So that's you can always do. There are many approaches to do this. What we are focusing is on precisely item collaborative filtering approach. Okay, so just to add to that, you can actually bring in neural networks into this. I mean, as an extension or build on top of this. Okay, but this actually doesn't require any knowledge of neural networks. Okay, there is no neural networks involved. But the second question, which is optimize this objective function over these vectors, these are m vectors, requires essentially define the, requires, there is no model here. The model is, so the model is hidden in this, I guess, vi transpose vj. Okay, that's essentially the model. So you have this loss function, which is a c function, and you want to find coordinates, the numbers of these vectors, such that the loss function is low. So whatever you computed, the xij's are the data. Okay, you computed the data once, pre-processed those, that matrix. Okay, and that's fixed now. Okay, that you're not changing that. You're not need to change the parameters. It's like saying I have training data. I'm not going to change training data. I'm going to change the weights of my neural network. Okay, but neural network has a specific form of going from data and parameters to loss function. Here, there is a specific form as well, except that the data and the parameters are not even getting multiplied with each other. Okay, the parameters vi and vj are just getting multiplied with themselves and then being compared to the data directly. Whereas in a neural network, you would think of, okay, there's some data that's getting manipulated by the parameters, w times x plus b, and then eventually some scoring function, y prediction minus y true or something like that, right? So that's not happening here. That's the only, I guess, conceptual block. Okay, but this does require knowing a little bit of the basics of either may not, yeah, I mean, PyTorch or TensorFlow. Okay, so the next 5-10 minutes, let's we'll run through a few basic ideas in PyTorch. Okay, for people who have not seen it, people who know stuff can chime in.
So,
Yeah.
gradient descent, we have to optimize within gradient descent. So here, weights will not come into picture.
The v's are the weights. Okay, weights are the parameters. Weights are just another name for parameters of my function, right? So v's are the weights here, or v's are the parameters here, and v's are the v vectors are the ones you need to optimize for. So you want to find the gradient of the loss function with respect to v's. Okay, and if you can find that, then you can do gradient update and keep changing the v vectors, and eventually you'll get a good set of v vectors which are which minimize the loss. Any other question? Yeah.
Can you repeat what you said about IJ? So it's not row, column multiplication?
Oh yeah, here you're asking about. So I just said, in the first step you compute, given the data, the raw data, group length data, you computed xij's, right? So those are some counts, right? Those are some integers. That's fixed. Now that's done. Now your model for predicting whether so you're trying to predict the counts actually. So in this problem, all you're trying to predict is, given movie I and J, if you really want to think in terms of prediction, given a movie I, given a movie J, how many people would watch it? Okay, so you know that number. The target is 10. How many people would watch it? Input is which movie and which movie. So the movie pair. And Vi and Vj are the parameters of the movies, whose inner product is what is predicting the count. Okay, so if you want to think in terms of a model, so f of movie I and J is trying to predict the count, right? Xij. Maybe this is 10. Okay, so the input is the movie indices. Okay, so that's why this problem is about embedding, right? So the input is movie indices. Movies themselves are not numerical objects. So you're going from movie names which are not numerical to things which are numerical. Okay, so this function is we are saying is nothing but Vi transpose Vj. Okay, in the sense that for each movie there's a corresponding vector Vi or Vj. Okay, these can be whatever dimensions you choose. There is some nuance in what dimension you want to choose, but if these are the vectors, then I'm saying that this is the model which predicts 10. Okay, but you don't need to interpret it this way as well. I mean, there's some. I mean, if you could think of in terms of pure optimization, v's, coordinates of v's are what I need to change so as to minimize some loss function. Looks like a squared loss function. Fine. Just do gradient update on the parameters here, which are v's. Okay, so these are, you can, for conceptual, you can think of them belonging to R2, which means that 2 dimensions. Okay, 2 dimensions. Let's say they're 2-dimensional vectors. then for every movie you can have a two-dimensional vector. Okay, that'll be in some two dimensions, right? XY plane, and then you can actually visualize which movies are close to each other and so on. Okay, those are vectors corresponding to movies, but your model for predicting whether a movie is liked by model for predicting the counts for a pair of movie is this, that Vi transpose Vj is my count for how many people would like this pair of movies. Okay, what is that count of people who like both these movies essentially. Okay,
XIJ is also.
so Xij is a target. Essentially think of Xij as your Xij is your ground truth, and the model's input as movie 1, movie 2, and there has to be a way to say what is the count, right? There has to be a mapping from movie names. Think of like, I give you two movie names, tell me what the count is. Like, what, that's the model we're constructing here. Okay, so actually I took too much time there. So I'm going to share another set of tutorials, and this is going to be a basic PyTorch tutorial. But so this I haven't shared this notebook online yet, but I'll share this. This is from I forget the name of the author, but I'll share the GitHub link on the syllabus page. So here they're just contrasting, what are the key modules that you want to import from PyTorch from Torch, and initially they contrast it with the NumPy. Okay, so torch.nn, which is where you'll get the nn module, nn.module, which is the base class from which you can extend to create other classes. Okay, uh, nn.functional, and torch vision. Torch vision is to get those things like data sets and data loaders. Okay, or maybe even transforms. I'm not sure. Uh, so what I want to get to, so this notebook has a lot of details, but I will get directly to um, okay, let me just spend some time on NumPy versus Torch. So if you actually Torch or TensorFlow, those are things that you should get to once you're comfortable with the NumPy version of your code. So for even small scale, small data version of your code, you should be able to write the NumPy version, in the sense that you should be able to manipulate matrices, and we saw a version of that in the first lecture, right? Literally, we did not do anything. We just literally hand calculated the backprop equation and did a for loop to get the classifier. So here, you're just comparing np.I is an identity matrix, and torch.I also gives you the identity matrix, right? So they're extremely similar. So the torch object, the tensor object, is essentially the NumPy ND array object, but with additional. It's kind of compatible with the NumPy ND array object, but it has more features. Okay, so random is fine. Like you can call dot shape to get the shape of your tensors, and in fact this is kind of critical. Actually, one of the key features for Torch is that you can, of course, push your data to GPU seamlessly. You can also debug your code using traces. Okay, you can set trace. I don't know if some of you have used Java, or maybe I'm not sure if Java you do that, but in C and C++ you can set trace and get into debuggers, right? So you can do debugging in Torch as well. You can push the tensor from CPU memory or the regular memory to the GPU memory. Okay, by using things like two CPU, two GPU, and so on. So if you want your computations to happen on the GPU, the neural network training, then you should actually put them on the device. Okay, there are some function calls you should do. So these are, this is just notation how to multiply things. I mean, even in NumPy, you can use x transpose x. It's just an example, but to multiply matrices, this is the notation you use. So with NumPy, you should be definitely comfortable with NumPy. So this should not be alien to you. Dot t is transpose at the rate, and then the other matrix. Okay, so this is fine. Another feature to save memory is to do a tensor dot some operation underscore. Okay, underscore gives you in place operation, so you can save memory that way. So in some code bases online, you will see people use tensor dot operation add underscore or something. Okay, underscore is the in place operation. Index in broadcasting is very similar to tensor NumPy. Conversion. So you can convert from tensor to NumPy, a dot NumPy in this case, or from NumPy you can make it a torch object. You'll do this so that you can push it onto device, for example. Okay, push it onto the GPU, for example. So now let's look at this notion of gradients, right? So instead of hand computing gradients, how does PyTorch? What is the PyTorch structure to get the gradients direct easily? Okay, what does PyTorch do under the hood? So although you will not do this explicitly, like import autograd, which is from Torch, we'll see how that operates. So let's say, actually, did I execute the whole thing? Maybe not. I don't need all this, but let's say. Okay, so w dot requires grad is the key flag that you need to flag it. So if you put any torch tensor and you do dot requires grad is equal to true, then if you do some other function calls, you will actually get the gradient of the final result. Wherever you do the function call, you'll get the gradient of the final thing with respect to this variable. Okay, that's the idea. So think of the final thing as like a loss. If you do loss dot backward, for example, you'll get a gradient with respect to any variable as long as its required grad is true. Okay. So W is a one-dimensional tensor. Here I'm just printing Z, and here you can see that because required grad is by default false, if you do some computation addition, total is the sum of two tensors, one cross one tensors. So that was a computation. If I want to find the gradient of the output, which is total with respect to its input, okay, any inputs whose required grad is true, because none of the inputs required grad is true, I got an error. Okay, and so now we are just showing that you can do that by setting explicitly requires grad is true. And you can get the gradient. Okay, you can get the gradient with respect as w dot grad itself. Okay, so it's the same operation that I did before, except that I added requires grad is equal to true, and I can get the gradient of the output with respect to its input, with respect to parameters which have requires grad is true. Okay, and you can also sometimes you'll see places where people want to compute with respect to variables, but they don't want the gradients to be locally computed. So behind the hood, as you do a forward computation, if requires grad is true, gradients will be kind of information that is needed for gradient computation is stored. Okay, so if you don't want such storage, then you can do a forward computation where you ignore. Okay, although I have told that these variables have requires grad is true, you can drop it by this torch.nograd context, and in that context it will not compute gradients. Okay, so let's directly go to the example where I want to show the structure. Let's see, this is all fine. So linear regression. So this is the example that we are discussing in the office hours. So this part is just data prep. Okay, so this is just saying from scikit-learn, there's a function called make regression which creates a regression example. In this case, I'm creating a 100 sample, 100 observations and one-dimensional data, one-dimensional features, right? So, and this is the data set, right? Did I execute this? Not sure, but okay. So this is the data set. Okay, x versus y plot, scatter plot. Now, next call is I'm converting the x and y to tensors. Okay, and then I'm actually creating a linear regression module. Okay, so the linear regression module is a class with subclasses nn.module, and basically you just need to define two functions. Okay, what's the first function is you need to initialize what are the parts of your linear regression model. Okay, it's essentially going to be, linear regression is just going to be one linear transformation, right? Beta transpose x. Okay, so here you can do that by saying here they've used actually nn.linear, so you should look up what nn.linear is, but you could have written here, initialize betas to be something, and in the forward pass you could have written beta transpose x. Okay, so you need to write these two functions where you initialize with some parameters and update. If you do a forward computation, we are making y prediction, that's going to be beta transpose x. Here, since it's a layer, it's beta of x. Okay, there's a bracket. That's the only difference. And then this part, they're just moving. They're figuring out whether the machine has a GPU. If it is, then you can do two device, as I said, two GPU or two CPU. I created a class called linear regression, so I create my model object is just an instantiation of that, and then this is the usual structure. So model is defined. That was a subclass of nn dot module. Optimization, there's going to be a call like this where you pass the model dot parameters, the things that you want to optimize. So model dot parameters is explicitly the things that you want to optimize. Okay, so for linear regression, it's going to be the linear parameters. Let's say if it's 10-dimensional regression, the beta 1, beta 2, beta 3, beta 10. Okay, and in this case, it's SGD optimizer, so it's also taking the learning rate. Okay, fixed learning rate. And the third thing you need to define is criteria. Okay, here we are using, so for criteria, the loss function, you can actually write your own function. You can write it in NumPy, the usual def function. Loss function is equal to with some arguments as input. You can do that. Even for model, you don't need to actually do nn.module. Okay, but it just makes life easier instead of calling autograd and all that. And here is this one executed. So here is a training, one step of training. Okay, one step of training. So model.train. So I'm setting gradients to be 0. Okay, and then I'm computing the loss. Okay, I'm passing I'm passing the 100 points, 100 observations, computing the loss with respect to predictions y underscores and true values y's, and I'm calling this key step, which is loss.backward. Okay, loss.backward computes the gradients with respect to current parameters, and optimizer step does that gradient update step. Okay, alpha or whatever this parameter, beta current parameter, beta new parameter is beta current parameter minus alpha times or learning rate times gradient, right? So, and then if you want to evaluate a model, then this is how you evaluate a model, where you don't care about the gradients. That's why there is this torch no grad context. Okay, and here's the plot. So let me run this. Okay, so we started with so this orange dots are the bunch of the original data, and the blue dots are my predictions. Okay, with my current model parameter. Okay, so this is one step of training that I executed from the cell. If you press Control Enter, you can keep executing the cell multiple times. So you can actually this. So you can see that the line is rotating, right? The blue line. I mean, I'm running it several times, but so you can see that the blue line turned. Okay, that's what's happening. So the key step is loss function dot backward and optimizer dot step. Okay, that's getting you the gradients and gradient updated parameters. So the only thing you have to now worry about is how did I set up the model correctly? Here we did use nn.module, so we extended that. So you need to read up a little bit of the documentation how to set the model correctly. But if you could set that up, then loss function definition and then loss function dot backward and optimizer the step will get you most of the way there. You need to put this in a for loop, right? As a for loop over epochs, and then take care of batch sizes and all that. So there are functions in this script, like which you should familiarize yourself with. like data transformations, data loader, okay, and data set. Where is this? This data set, data sets. That's helpful for vision. Similarly, for text, there is torch text, and that's that example you saw in the CNN example from last time, right? If you open that notebook, they are using torch text based utilities to deal with text data. But ultimately, once you set up the data, whether it's images or text, the key steps are the ones I mentioned: set up the model, optimizer dot loss dot backward, and optimizer dot step, right? That's the thing. So I'll give the link on the syllabus page, so to go through this, and that's it for today. Ask me questions if after this. We have lab sessions. What is it? Yeah, so the TA is gonna talk about assignments and solutions of assignments in labs, right? Is she not doing that? Yeah.
I think someone asked this already, but go back to question one about fine-tuning extraction.
Yeah.
So feature extraction, let's say GPU, takes a while.
Oh, feature extraction takes a while. Yes, because that's happening on the. It may be happening on the GPU. Sorry, on the CPU side. So you're reading image from disk, passing through your network, and getting that feature vector. Yeah, it may take more time because the number of parameters is high. Even. Sorry, I can't hear you. Yeah. No, it doesn't. So this example, this convolutional classifier example, is actually taking the same ResNet 18, but it's only training on 100 examples. So it's very fast. No, for CIFAR 10 it could take 2 hours. Sorry, I can't hear you. Can you come over and